Alright, so today we're going to be going over basically all the operations that we'll be using in HSM Express and what each of the parameters it needs, each operation needs in order to give you the correct G-code and toolpaths. So the first operation we're going to start with is face. So what face does is it'll take a cut across a face and take off basically however much material you'd like down the entire face, and it uses a really simple toolpath to do that. So we'll go ahead and select the only tool that we have, which is our 4mm end mill. We will go ahead and select our contours, which will just be this face and this face. We'll go ahead and set our depth. Now we don't want to take a lot of material off this thing, we just want to face the edge of it off. So what we'll do is we'll take 5 thousandths. So that'll be our cut. Now the parameters that we can give it, we'll give it a 10,000th of tolerance. It defaults to engaging 95% of the tool, as it says there. The step over is basically talking about how much of the tool is going to be engaged at once. So, if you have our tool is 0.1573 or something along those lines, it's going to engage 0.1496 of that at any given time. Now, so if we had like a half-inch tool, we could probably engage 0.375 of it at a time, or 3/8 of that tool at one time, and it'll still be okay. You normally don't want to engage any more than about 3/4 of a tool, or you'll get some serious issues regarding chip clearance, especially if it's a slot. But for right now, we'll just leave it at 0.70. That's fine for right now. This pass direction will actually rotate all of your passes to a set angle. So if you want to, give the part a different pattern rather than just, straight moving across this way, if you want it to move this way or something like that, you can just rotate the toolpaths and it'll let you do that. Now, pass extension and the stock offset basically do the same thing. It'll artificially inflate the stock and basically make it so that you can machine more of the face that you want. So if for any given reason you wanted to machine more than just this face, if you wanted to move off of this face a little bit and come out to here before you went back into the material on both sides, you could do that with both of those options. Multiple depths is if you wanted to take this in multiple passes. Let's say you wanted to take 1/8 of an inch off your material. If your material was pitted really badly and you wanted to face off, 1/8 of an inch to get a clear reference surface, you didn't want to take it all at once, you could take it in several passes. But since we're only taking 5 thousandths off, we'll be definitely okay just taking it in one pass. Direction both ways. So what the direction of a cut means is whether you're moving climb or conventional. Now, conventional milling is basically the cutting flutes will, in this case the single flute that we have, will engage the material at the thickest point at first and then move to a thinner, conventional milling will engage in a thin chip first and then get thicker as the cutter moves through. So what that means is that we will be basically taking a really thin chip at the start and then it gets thicker and thicker as we move. That's called conventional milling. As you can see it there on that little diagram, it starts out thin and then gets thicker as it moves through the material that direction at that spindle orientation. So it looks like it's moving clockwise and moving to the left. Now, with the spindle still moving clockwise, moving to the right instead, we get climb milling, where the tool will engage the thickest part of the cut first and then move to the thinner part. Now, there's advantages and disadvantages to both. Namely, conventional milling is generally easier on the machine and the tool, but it leaves a poorer surface finish. Climb milling, however, is much harder on the machine and the tool, but leaves a pretty superior surface finish. Now, since we're doing light duty work and really our machine and our tools can take it, and we're not aiming, for super ridiculously long tool lives and stuff like that, climb milling works just fine for us, especially with the depth of cut that we're taking. We're not doing anything crazy. So really both ways will work just fine for a part like this. Stock to leave. We don't want to leave any stock, so we'll leave that disabled. And linking. Basically here we'll do we did this last time, 150 inches per minute. We'll change this to 2, and then everything else can just stay the exact same. So it'll generate a toolpath, and we can see that it faced off the entire face of this part here. And what we're going to do, we're going to go ahead and simulate this. So we'll show our stock, make it very good, and go ahead and start. So as we can see, it's going to start over here and move through and face this entire part off. Now pay attention that we're actually removing some material in this other slot that we have to make. Just something to keep in mind. That when you're doing simulate, you do want to watch and make sure that your machine is doing what you tell it to do. So I'll speed this up a little bit. As you can see, it goes through and is cutting all of this off. Very good. It's actually straining my computer a little bit, so I'll go to good. So you see, basically just taking 5/1000ths off of the entire face here. I think you guys get the idea. Now we can see that this operation is going to take 14 minutes. So that's facing. Next, we've got two different methods of creating pockets. We've got 2D adaptive and 2D pocket. So this is the adaptive strategy, and this is the legacy strategy, and we'll explain what both of those mean as we go through them. So let's start with the adaptive strategy. So we've already imported our tool, so it already has all of our cutting feeds and speeds in there for us. So go ahead and move to our model, and we'll select our contour that we want to machine. And then we'll go ahead and say that from this contour we want to go negative 1/4 of an inch, which is what the model calls for. That's 1/4 of an inch lower than this face. So this is 1/4 inch lower than that, so we want to go down 1/4 of an inch. So our 2D adaptive clearing, basically we'll set everything to the exact same as we did before, 1/10,000th, and our step over here, our optimal load. Now this is not called step over for a good reason, and we'll see why it's not called that after we simulate this. So we'll just set that optimal load to 70/1000ths. And again, our minimum corner radius and stuff doesn't really matter all that much. We'll take this in multiple depths because 1/4 inch is quite a bit to take all at once. We'll do it in 1/8 inch increments. And that should be fine. And our direction, we'll go ahead and keep it at climb because the machine can take it, and we don't want to leave stock, so I'll go ahead and uncheck that. On our linking, which again will determine how we're going to do rapids, we'll change it to always use our high feed, and we'll change our high feed rate to 150 inches per minute. We'll also take our maximum stay down distance to 2 inches to let the machine kind of stay down into the cut more. Because if we don't select stay down level most and give the stay down distance 2 inches on a cut like this, basically what's going to happen is anytime the machine needs to move more than 2 inches, it's going to bring the tool all the way up to the retract height, move it, and then bring it back down. And that can waste a lot of time. And so this is also our lift height. So if we're not going to fully retract, but we just want to lift to move to our next position, we can go ahead and give that a distance. But since you want to keep the tool down inside the cutting zone most of the time, we'll leave that at 0. This is our non-engaged feed rate, so we'll keep that at 150. Since it's basically the same as rapids, we're not cutting, so we can move pretty quick. And we'll leave all of our lead in, lead out stuff to be calculated by the machine. That we can go ahead and keep. So we'll let that run. Now, this is a really advanced method of cutting, so it's going to take a lot longer to generate your tool paths, which really you shouldn't notice that bad, but it's just something to keep in mind. Okay, so it's done. Now, the reason it's not called step over and is instead called optimal load, we'll see right now when we simulate this. So I'll go ahead and simulate. We'll show the stock, show very good, and run it. So as you can see, it's going to do its normal helix into the tool, or into the material, and start ramping out in that kind of helical motion. Now notice, it's not taking, it's not stepping out, doing the whole cut, stepping out again, doing the whole cut. it's always keeping exactly 70 thousandths of the tool diameter engaged all at once. There's never not 70 thousandths of this tool engaged when it's running at the cutting feed rate. So right there, it's always keeping 70 thousandths engaged. Now the reason it's called adaptive is because the machine will adjust the tool path in order to always keep 70 thousandths of this tool engaged, or whatever optimal load we set depending on the tool and depending on how heavy of a cut we want to take. So it's in a lot of ways more advanced than the legacy clearing, which we'll see on this other pocket we'll make over here. So it's going to go ahead and cut through and move through all of these side pockets, and it'll go do its second cut, and we'll see that that takes 6 minutes and 45 seconds to complete. Now the other method is the 2D pocket. So it's already got our tool information, so we'll keep that. We'll go ahead and select our contour and get started. So from the contour, again, we want to go down 1/4 of an inch. From our 2D pocket here, we'll want to set our tolerance to 1/10,000th. We'll want to take our, this is step over, right? It's not the optimal load. So we'll give it 70 thousandths again. Multiple depths, because we do not want to take this all at once. 0.125. All this stuff, you can kind of experiment to find out what it does, but a lot of it's pretty self-explanatory. Stock to leave, we don't really want to leave any stock, so we'll be fine with that. Again, we'll have to change all this stuff in here. That's fine. And our lead-in we'll keep the same. So we'll let that generate, and you'll notice that that looks a lot more simple than that. You know, it's not as advanced of a tool path, and we'll see that when we're letting it cut. So we'll go ahead and simulate. Show stock. So it's going to helix in, and what you'll notice is that it takes a lot of the cut at once. It engages basically the entire tool here. Now, what that means is your tool is going to take a much greater load. It's going to, ask a lot more of that tool to not break when it's engaging basically the entire diameter. While adaptive never did that. Adaptive never made the tool engage greater than 70 thousandths. It never would do that because it's adaptive. It's smart enough to know not to do that. Now, once it's cleared it, this is pretty decent at not engaging more than what you want. But you'll notice it does what any other pocket would do. It steps out, takes the profile, we'll step out again and take the profile, and we'll just do that until the entire profile has been completed to the correct depth. So this is actually a lot harder on the tool than the adaptive profile was. But we can see that it's a bit quicker. Oh, actually, this is slower. It was quicker when we did it before. I think that's something to do with our rapid rate. But basically, this usually will yield you quicker cycle times, but in this case it didn't. I think it has to do with the rapids that we used for this other pocket here. But this will actually put a lot more load on your tool and will actually have a greater risk of snapping it. Oh, that's why it takes longer. So this is a good part about simulating, is we can see what it's doing. So it took 1.15 on its first cut. Well, we wanted to take 1.25, or 0.125, excuse me. So go here and say, oh, we made a typo. And that's the good thing about simulate, is I saw, why is it taking 0.115? It should never be taking that Z depth. And so now I'm going to edit here, or not edit, excuse me. We'll want to simulate. This should be quicker. Right, 5 minutes 17. So we've shaved about 1 minute 30 seconds off of our adaptive. However, this is going to load the tool up much more. See where those steps are? it steps out, takes the profile, steps out, take the profile, steps out, take the profile. This will just keep 70 thousandths engaged all the time. This will keep 70 thousandths, step out, keep 70 thousandths, step out. So one is a lot more advanced. Basically, 2D adaptive is better for like weirdly shaped pockets like this. And it's basically made possible by just having a more advanced CNC control. Ages ago, CNC machines couldn't handle doing things like this because it was, you'll notice, this toolpath is 1.2 megabytes of code because it's a lot more complicated. CNC machines couldn't handle that much data, and they couldn't do it as quickly as adaptive clearing would need it. Regular legacy clearing, though, was simple for CNC machines. It's 99 kilobytes. It's about 100 times smaller than this. Or 10 times smaller, 10 times smaller than this. In just raw data that goes to the machine. So it's simpler, yes, but it also does wear a lot more on your tool. Now, since we're not a job shop and we don't need to worry about, extending those tool lives as long as humanly possible, we really can use either one. It really just is a matter of preference. I personally like the adaptive for shapes like this. It might be a bit slower, but it is a lot safer, and you'll generally break a lot less tool bits doing it this way. But again, it's just a matter of personal opinion. If you program either one correctly, you should be fine. So next we're going to go over 2D contouring. Now what 2D contouring does is it will take an edge and, contour it. It will follow the edge. Again, all of our feeds and speeds are already set because we've already selected our tool. So we'll go ahead and select this edge. Make sure we're propagating on the Z. So go ahead and select all of that. And so we'll notice that we have this little black arrow inside our stock, not inside the slot that we want to remove. And so we'll see that a bit later. Now I happen to know that this cut is 1/8 of an inch. So we'll take it negative 1/8 of an inch. And now it automatically selected climb for us. And we're just a couple things you have to fill out here. That's fine. Again, these are fine. These minimum radius cuts don't really matter for a cut like this because it's a straight line. This is our finish overlap, so how much farther do we want to go past our starting point. And we've also got our tangential fragment extension distance, which is basically just a fancy way of saying how much farther do you want to go. We don't want stock to leave, that's fine. And again, we'll come in here and do our adjustment of rapids and all that stuff. We'll leave all this the same. So we'll go ahead and run it and simulate. We'll go ahead and run it. Now right there we can see we have a problem. It's cutting on the wrong side of the contour. We don't want it to cut that side. Because we selected climb milling, it is cutting on the wrong side of the contour. Well, it has to either do with the fact that we selected climb milling, or we can also go to our contours here and that option is not for contouring. Okay, so it has to do with the fact that we're doing climb milling. Now if we changed it to conventional milling, then it should, in theory, work correctly this time. It should take the correct material out, which it looks like it will. So go ahead and show stock. And advance. Yep. But it looks like it's taking too much. Right? I mean, it's taking more than it should, and it's leaving. Well, that's normal. It should leave that there because it's just going to contour those two edges. But we'll also see that it's leaving this part here. If we wanted to break these edges, we would want to artificially kind of increase the length of these. And we can do that on our tangent distance here. So we can change that to 1/2 inch. And we regenerate toolpaths. And we simulate. And show stock. This looks like we didn't quite change the right. And this is all part of it, is making sure you're using the right settings. Make sure you simulate. Make sure you're running everything correctly. Otherwise, you'll run into big issues like this where, the operator doesn't know what the problem is. And so when he tries to run it, it's just going to not work and you're going to get bad parts. So I'll try to change this setting here inside the actual the passes menu and see if that does. So it looks like it's still coming in the wrong area. And again, we'll go ahead and check and see that it should be doing it the right way. You can try to change this tangential extension. So that didn't do it either. I think that's something to do with the fact that it is selected a closed contour. If this were an open contour, that might work better. So we can go ahead and try that. Selecting an open contour rather than a closed one. If we just select this and this, and then we add that 1/2 inch. There we go. However, it is now going to the wrong depth, and it's cutting in on this side. So this is one of those things where the machine doesn't know what cavity is what. It doesn't know that it needs to machine this. All it knows is that there's a line here and a line here, and it needs to contour them. So it is just a matter of kind of messing with the settings and making sure, simulating and making sure this does what you want it to do. This operation is a bit finicky, and you will need to mess with it in order to get it to do exactly what you want it to do. So this one you'll need to kind of play with yourself and kind of get a feel of what each of those settings do on a kind of case-by-case basis. Because this is one of the complicated ones where you've selected a contour, but it doesn't know which end it needs to be machining, where with like a pocket, where it's a closed contour, it knows exactly what it should be doing. So it needs a lot more information and a lot more kind of operator interpretation to figure out what needs to happen. Next, we'll be going over bore. Now a bore, we'll go ahead and bore out these next couple holes here. So I'll go ahead and select these holes here. Now as you can see, it already generated a toolpath because bore is a very simple operation. It is just going to go and core out this hole to the full depth that this allows. Now what we really need to look for here is the passes. We don't really want, well, what a bore will do is it will just take the hole and punch out what's called a slug. It won't make a pocket per se, but if we were going to, say, make a hole here, if this hole was larger than the tool diameter times 2, it wouldn't make a I'll just go ahead and leave it. So you notice it doesn't need to clear out. It clears out the entire hole, doing basically the helix that it's moving in. But if we were to do a bore on something like this, it would basically contour it and leave the slug to fall out. Now we don't do that on larger holes because that's dangerous. That slug can go flying and hit something or someone. But a bore on smaller holes like this will give you the desired effect of basically making a hole. And it's basically got all of the same things you need to edit. The thread pitch will basically define how quickly is it going to drop into the material. The default is calculated based on the tool and what you want the ramp and feed rate to be, so you can leave that. You don't need to mess with that one. Now, the circular, what this one does is a bit different. You can see it's already making tool paths for us. Now this is similar to the bore, but it kind of does the opposite. Rather than you defining the number of steps kind of horizontally, let's say, if you're looking at it like this, if those multiple passes on a bore would increase the number of passes it would take horizontally. On circular, your multiple passes will do the same thing here, but it will be also you can do multiple depths. So for cutting large holes, you'll want to do circular rather than bore, because a bore is meant for just resizing a pocket per se. Circular is meant for creating a circular pocket. Bore is meant more for finishing off an already created pocket on like a casting or something per se. So for making holes like this, you'll want to use circular. And this step over, again, you'll just change to 070. And then this, the roughing step down, you can change that to 0.125. So basically that will just take, oh, there was an error. I think it has something to do with this, so we'll just let that reevaluate. So we can't do multiple passes this way, right? Because the bit isn't big enough to do multiple passes. It can only do one pass. That's why it was giving us an error. So we can go ahead and do circular. But one thing we'll notice is that this might take a bit longer because it has a lot longer toolpath. So what we'll do is we'll go ahead and edit this and deselect one of these holes. So they both do the same number of holes. And we'll compare and edit. Or we'll just simulate both. So this will take 31 seconds. And this would take 28 seconds. So the difference isn't huge, but it's, again, because these features are really small. If these were larger features, bore would be much more efficient than circular, but you'd be fine using circular for just about any of these smaller holes. Because the bits we're using are small and the holes we're using aren't much bigger, it really doesn't matter which one you use. If you were machining out something like a bearing seat in a plate that's, 1 inch bigger, 1 inch or bigger, then you'll want to do a circular rather than a bore, because a bore will just cut out a giant slug and then hurl that across the shop somewhere, and we don't want that because that will lead to injuries. You'll want to use a circular for something like that to create a large circular pocket. You could also theoretically use adaptive clearing or 2D pocket. There's a lot of methods you can use to reach any of your goals you want, but realistically, one of them is going to be quicker than the rest, or easier to program than the rest, or what have you, and it all just depends. So I do recommend just making a bunch of odd features like this, just play around and see, get used to using these tools and simulate. Use that tool that lets you simulate and figure out what's quicker, what's quickest, what's the best to use for different things, different kind of operations we'll be doing. So that was just a quick overview. Really, it's hard to convey exactly how or when you'd use each of these. Really, it just takes some experience. So get your hands dirty, go play around with this cool software that we got, and basically, yeah, just get your hands dirty and try new things. Try camming out whole parts and simulating. We could go here and simulate the whole part and see how long the whole thing would take. And see, play around with the parameters and see how we can get this to run faster, more efficient. And you'll learn a lot about machining that way too. And again, do feel free to ask questions in our Slack. I'll be glad to answer. I don't know what all of you guys know, where the baseline would be, so knowing what you guys are confused about would really help me kind of convey these ideas better. So thanks for watching, and get back to work.